The University of Lethbridge continues to train the next generation of thinkers, teachers, and builders. One area of study that may boggle the mind but also advances thought and theory in our modern world is the study of quantum physics. Joining us today to discuss the ideas and the science behind this field of study is Professor Saurya Das. Professor Das, welcome to Bridge City News.
Thank you very much, Devin. Thanks for having me.
So, Professor, can you explain the fundamental principles of quantum physics in simple terms for our viewers who may not be familiar with the subject? And maybe just go into what the word quantum means, because I've heard quantum physics, quantum mechanics, quantum computing. What does all this mean? Put this into layman's terms for us here.
Of course, I'll try my best. So, at the fundamental or the subatomic or the very tiny levels, the nature and physics works a bit differently than we see around us, which is very smooth and deterministic. At the subatomic level, nature is more probabilistic and uncertain, but that's the fundamental law of nature. Therefore, it affects everything that we see around us, like computers and what have you, like our cell phones, GPS, everything is determined by quantum mechanics. But although since it operates at a very small scale, we can't really see it with our naked eyes. So that's the fundamental nature. And quantum, the word quantum means it's related to the word quantity, because at the fundamental level, things aren't that smooth. It's always in terms of quantums, like packets of energy, packets of momentum, packets of charge, and that kind of thing. So that's the origin of the word quantum, and being ubiquitous, it's kind of applied everywhere as it should be.
Okay, so now that we know the word quantum, can you just tell us what the purpose of studying quantum physics and quantum theories is all about?
Because, there at least two ways of looking at it. One is to answer the fundamental questions of nature, which as human beings, we have always been curious about for thousands and thousands of years. Like, for example, where did we come from? Where are we going? What's the universe made up of? What are its constituents? And how does basically everything work? Why do we have 3 space and 4 dimensions? Why not something else? Why do you have 1 time and not 2? So these are fundamental questions that often we take for granted. But so to answer these questions, we have to invoke quantum physics, because that's the fundamental thing. So if we want to ask fundamental questions, we have to go to the fundamental theories of nature or fundamental ideas. That's one way of looking at it. Other ways, like although these questions are fundamental, they have always been applicable and applied to technology. And modern technology, like computers, electronics, they cannot do without quantum mechanics.
Okay.
Therefore, that's the other motivation, that fundamental physics advances may not the advantages may not be obvious now today, but very shortly thereafter, usually they become applicable to technology. Most of them anyway.
And then, how does the study of quantum sciences advance the mission of the University of Lethbridge then?
Well, University of Lethbridge is first of all a university, which means that the pursuit of knowledge, pure knowledge, just for the sake of pursuing, that's one of the tasks of the university, right? To push the frontiers of human knowledge, so to speak. So that is a very strong motivation. Also, being fundamental questions that are being or would be answered, it's going to have impact in the training of our students, the potential of our students of being useful in science, in society, everywhere, because this is like very good training. It would attract the best minds, very first-rate minds to this university to enhance the research reputation that it already has. But it will certainly add to that. And as we have more people, first-rate, very good scientists and everything, they will attract more students and researchers. So it's it's a growing kind of thing. So it's going to definitely continue to enhance the university's reputation, and it's in line with the university's plan and everything.
So let's talk about quantum entanglement, because it's often been described as a spooky action at a distance. Can you explain this phenomenon and its significance in the field of quantum physics?
Yeah, so quantum entanglement, that's a great question. So entanglement is one way of thinking why quantum mechanics is so powerful and is going to affect computers, for example. It's going to make computers like billion, trillion, zillion times faster. It already is, right? And the reason is that, of course, it's more powerful than classical computers. And the power one way of thinking of it is that the power comes from entanglement, which basically says that all the atoms or whatever the fundamental entities are, they're all linked to each other. It's very difficult to extricate one from the other. And one way of saying is like when you put things together, the sum is bigger than its parts. So entangle means, right, like since the atoms and everything can now talk to each other, they can share resources. So they can share resources, like you have it's like, instead of, 5 people working in 5 different, locations, they join forces, and then it becomes much bigger than the whole. So entanglement is one way of thinking of it, and it's very quantum, therefore. And there you go. It kind of says why quantum mechanics is powerful.
So is this how we can get faster processors? We can get larger memory cards or like bigger like chips of RAM in our computers?
Yeah, one can think of it that way in terms of the final, computing power. Quantum computers would work in a little bit different way. So thinking of in terms of, regular chips and RAM, we have to extend our kind of way of thinking or understanding that a little bit because it'll have other components, quantum components, right? Like newer quantum components. But in the end, yes, it will be an immensely powerful. So it can do computations, calculations at speeds which are kind of almost unthinkable with classical computers.
Wow. Now, what are the current advancements or breakthroughs in the field of quantum physics that have the potential to revolutionize technology or our understanding of the universe?
Of course. So quantum mechanics, as I said, it's fundamental. It works everywhere. As I mentioned, it works at the subatomic scales. It works at the fundamental universe scales as well. When we look at cosmology with telescopes at very large distances, cosmic distance scales. So the advances, there has been lots of advances in the last 20 or 30 years. That's why it's often said now we're going through a second quantum revolution. The first quantum revolution was when quantum mechanics was first proposed and formulated. And the revolution includes things like lots of new results in quantum computation. Now quantum computations are closer than ever to being actually realized. There are already operational quantum computers here and there, not scaled to the extent that we would like to, but proof of principle, that they've shown that it works, right? So breakthroughs in theoretical side, like the way we can use quantum computers, breakthroughs in the actual practical side of making of quantum computers, and thirdly, when we apply quantum mechanics to the whole universe, there are lots of new results, interesting things, observations which have come in the last couple of decades. So there has been a lot of advances, and that's the reason why this is kind of the right time.
Now, quantum physics challenges our classical understanding of cause and effect. How does the concept of probabilistic behavior at the quantum level relate to determinism and the nature of reality?
Again, that's a very good question. So the complete predictability that we see around us, for example, if I drop something, it's predicted that it falls, right? It doesn't. Right. Or if I hit against the wall, I'll come back this side. So these are in a way of saying these are approximate things that we see. This is a kind of approximate a consequence of quantum mechanics. But if you go down to the fundamental, again, the atomic level, these things often don't work in the sense like if there's a wall there and there's an electron kind of hitting the wall over and over again, there's a 1 in a million chance it'll actually appear just on the other side. Like it'll just pass through the wall. Mm-hmm. Okay, and so that's what happens. What happens is when you look at big systems like us or this room, these spooky effects, these non-intuitive effects, kind of become smaller and smaller and smaller. There's still a little bit of chance, but that I might go on the other side, but the chance is really small. So in a way of saying is what we see around us is an approximate view of nature. The exact view is the quantum view, and that's why we call this intuition, I guess, what we see around us.
So you're talking about nature here. Can you give us a description of the 4 forces of nature and how they interact in the realm of quantum physics?
Yes, absolutely. So there are, interestingly, we see, we can say there are lots of forces in nature. We see, a force when we pull something or we push something, but fundamentally there are just 4 forces in nature: the gravitational force, the electromagnetic force like magnets and stuff and charges, and the strong nuclear force and the weak nuclear force, which hold atoms together, which binds atoms together and things like that. So they're just 4. And fundamentally, since everything has to be quantum, these forces must be described by quantum mechanics. One of the problems is that gravitational force has kind of stood aside it has kind of stubbornly resisted a quantum description of nature. That's one of the things which physicists are working on. But the goal, the holy grail of theoretical physics, if you like, is to try to find a theory, just one theory which explains all the four forces of nature. It has not been done so far. So we are kind of stuck at 3 on one side and 1 on the other side. But that's the hope, hopefully.
So we're talking about numbers right here. Nikola Tesla talked a lot about the numbers 3, 6, and 9 in his work and research. Are there significant number sets in quantum physics?
Well, there's a reason, for example, why we have certain things. It has to do with symmetries, the underlying symmetries of nature. So there's some explanation of the numbers, not all. I'm not sure if Tesla's 3, 6, and 9 are directly related to what we have here. But, often there are underlying, we say symmetries or underlying views of nature which predict certain numbers. That's often the case. And that's one of the goals of physics as well, to see why certain numbers are the way they are. Sure.
Okay, so can you just give us a brief understanding of the difference between the computers we are used to and quantum computing?
We know of parallel processors, right? So my computer here probably has 1 processor, but you can have 8, and then 8 of them, work in tandem. They work together. Supercomputers may have, 50 maybe. But you can think of as a quantum computer as like having 1,000,000 processors, or maybe 10 million or 1 billion. Of course, physically, you can't have 1,000,000 processors, right? I mean, 1,000,000 is too many. It will probably occupy this whole city, and then you have power, and it's heating up and all that. It's not practical, right? But quantum mechanics, because of entanglement, because it connects every piece with every piece else, it kinds of like that effectively you can think of the number of processors as growing exponentially, really, really. So even within a small quantum computer, it can be this big or whatever, within a reason. But effectively, it could behave as something which has 1,000,000 processors. And if you have 1,000,000 processors effectively, although we don't actually have 1,000,000 pieces inside, it's quantum mechanics, the miracle of that. You can accomplish a lot of things. For example, factorize large numbers, or in a fraction of a time. Some of the things that classical computers can't do are useful, for example, in e-commerce, like credit card numbers can go from one place to another without being, eavesdropped, because you can't do certain things. It'll take infinite amount of time. But with quantum computers, you can do it just like that. So there could be issues, challenges associated with it as well, like security and that kind of thing.
So you've touched on this throughout our interview, but can you just explain or summarize how the quality of life here on Earth will be better improved through the study and implementation of quantum mechanics and physics?
Yeah, well, it's in the end, there is this huge amount of resource that's out there, quantum resource. So it's kind of a resource that's not been tapped, broadly speaking. So anyway, we can tap this, not just a small resource, this huge amount of resource for computation and other stuff. Any amount of resource that can be used, fairly equitably, and that sort of thing for human, development or growth or happiness is a good thing. I think it's just like another very new kind of resource. It's like another source of energy, if you like, which has never been tapped. So, and it's, as far as I can see, the source is practically infinite. So that's ought to have an effect on, if used properly, of course, on human, betterment, I would say.
Well, Professor Daz, that's all the time we have for today. Thank you so much for being with us today.
Thank you. Thank you for having me.